A common way to interact with hardware is through a memory mapped register. This is a hardware register that has a mapped address in the address space of the system. To interact with the hardware, the programmer can use a pointer that points to that address to access individual bits of the hardware register. In this video, we are going to see what that looks like from a hardware perspective, explaining what a possible memory mapped interface might look like and designing our own. We will develop a simple interface in Verilog and write C code that interacts with our Verilog code in a way that a processor connected to our custom hardware might. Say we have some 32-bit registers that we want to be accessible from software. To do this, we will have to connect to the overall memory subsystem. A typical, simple interface for this might look like the following. We have an address input, which will be used to select which register we are going to read and write to. A data input, data in, which carries the data that we might want to write into a register. A write input signal, WRN, which indicates that the interface wants to perform a write operation. A read input signal, RD_in, which indicates that we want to perform a read from a particular register. A data output, data out, which carries the data that we are reading out to the interface. And finally, a read valid signal, RD valid out, which is high when the output data is valid. Let's first look at a signal timing diagram for this to see how these signals read and write to internal registers. As this is a synchronous circuit, we need a clock and a reset. I've omitted the reset from the timing diagram, but we will consider it in the Verilog code. Let's say we have an internal register, reg04, with the address 0x0004. And let's say that we want to write to this register first, then read the value that we just wrote. Initially, reg4 is in an unknown state, so we have a bunch of x's. To write to the register, we need to do a few things. First, we need to set the address input to the address of the register, in this case, 0x04. We need to set the data in to the data that we want to write. Let's write 42. And we need to set the write input signal, WRin, to high. As this is a synchronous circuit, we can see that on the following clock edge, the value 42 is saved in our register reg04. Okay, great. That is the basics of writing to a register. Now let's consider reading the value out of this register. To read the value, we again need to set the address input to the register that we want to read. However, this time, instead of the write input being high at the same time as the address, we need the read input to be high. The memory controller will now wait until the RD valid signal is high, indicating that the data out is carrying the correct data. This is a very basic interface, and it resembles the Lite common interfaces used by Intel and ARM on their devices, such as Axie or Avalon. However, be warned that a memory mapped hardware interface might not always look quite like this. There can be subtle differences depending on the type of memory controller you are connected to. But this should give you a pretty good overall feel for what the interface looks like. Okay, now that we have a good feel for the timing of our interface signals, let's think a bit about the structure of our circuit and how we can code that up in Verilog. We shall start with the write interface to the module and then focus on the read interface. At the center of our module are the registers that we want to read and write to. Let's say that we have two registers, reg1 and reg2, and we're going to give these 32-bit addresses. Let's give reg1 0xFFFF0000 and reg2 0xFFFF0004. So those are two 32-bit hexadecimal addresses, like you would see in the other parts of the course working with your microcontroller. We only want to write into these addresses at particular times when the address appears and when the WRin signal is asserted. So each of these registers will have some sort of write enable input, where the value is only updated when the write enable input is asserted. Okay, so now we can connect the data in to each of our register inputs. However, then we want to be able to selectively set each individual write enable bits of the register depending on the current address input. We can do this with something called a demultiplexer. A demultiplexer can be thought of as kind of the opposite of a multiplexer. Basically, this is a unit that has a single data input, a select input, and a bunch of outputs. Based on the current value at our select input, we route the input signal to one of the outputs. So we can use this to route our WR_in write signal to each of the registers based on the current address input. Okay, let's describe the write interface for our memory mapped I/O in Verilog. First off, we need to describe the actual registers that we want to read and write to in our hardware circuit. We can write logic 31 down to 0 reg 1 to create a 32-bit register, register 1. And then logic 30-bit down to 0 reg 2 to create a 32-bit register, reg 2. The next thing that we want to do is assign a value to these registers. Remember that a register is a clock sequential circuit element, so we need to use an always underscore FF block. So let's write always underscore FF at pos edge clock begin. This is in the usual way that we've done in the previous videos. Looking at our circuit, we want to assign the data into either of these registers based on the value of the address input and the WR in signal. We can see that for both addresses of our registers, the first 16 bits are common. Let's create a simple if statement to check if that is true and if the write signal is asserted. Okay, for the remaining address bits, we either want to write into reg 1 if the bottom 16 bits of the address are 000, and reg 2 if the bottom 16 bits of the address are 0004. Let's use a case statement to do that. So we'll write case, address in, 15 down to 0 to get the bottom 16 bits. When the bits are 0000, we want to assign reg 1 the value at data in. When the bits are 0004, we want to assign reg 2 the value at data in. Okay, great, we're almost done. However, we have one small thing that we are forgetting. We need to initialize these registers when we reset the system. So we can write if reset reg 1 is 0 and reg 2 is 0. That should hopefully now describe the write interface of our memory mapped circuit. Now let's look at the logic for reading the registers. On the read side, instead of a demultiplexer, we need a multiplexer. We have many inputs and one output. The multiplexer will use bits of the address to select which output goes to the registered data out signal. To comply with the protocol, we also need to output a read valid signal to say when the data at data out is ready to be read. As the data out signal is registered, it takes one clock cycle for the output data to change according to the input. So one way that we can synchronize our valid signal is just to register the RD underscore in signal to match the delays. Now let's code the read channel up in Verilog. Again, this involves assigning to registers, so we are going to use an always underscore FF procedural block. Let's start with the RD valid signal. That is just a registered version of the RD underscore in signal, synchronizing the RD valid signal with the data that's being outputted. So we can just write RD underscore valid underscore out, blocking assignment RD underscore in. Okay, now onto the read side, which will be quite similar to the write channel. We have the same if statement to check the top 16 bits of the address. However, this time, instead of a WR underscore in signal for indicating that we want to write, we are conditioned on an RD underscore in signal. Then, like before, we have a case statement for handling the bottom 16 bits of the address input. So we can write a case statement where if we see 000, then data out is assigned register 1. As if we see 0004, data out is assigned register 2. Remember, we registered the data out signal because this is an always underscore FF block. So we need to initialize it with a reset condition. And that should describe our memory mapped register interface. Let's simulate it. We can see in the waveform that we are writing to reg1 the value 42 and then reading it, and the circuit responds correctly. But let's change this. In the project directory, we can actually change the code that is reading and writing to our hardware interface. If we open the file software_driver.h, you will see the code that I'm referring to. This should look reasonably familiar to you, as it is modeled to look like the Arduino sketches that we've been writing in other parts of the course. We have a setup function that is run once, and then a loop function that is called continuously. We also have three functions: regWrite, which we can use to write to a register, regRead, which we can use to read a value from a register, and exit, which we can use to end the simulation. In essence, what we are doing is modeling both the hardware peripheral on an Arduino device and simulating it, along with the code that is executing on the processor of the Arduino device. Let's change the read and write command, so instead of reading and writing from reg1, we are doing it to reg2. Reg2 is mapped to the address 0xFFFF0004. So we can change the address that we are using in the regRead and regWrite functions to change the register that we are interacting with. Let's make that and simulate it. Great, we can see that we are now interacting with the other register. Excellent work. This was a tricky one. This is a more substantial sequential circuit. So maybe take some time to go back and re-watch this video to make sure that you understand it. We will be using this as an interface to some of the later videos and questions when we're interacting and testing our hardware. Okay, see you next time.